Students, rename with your register number and your name. Students, ask all your students to join immediately because I have to start the class by 6 p.m. And first we are going to see the first unit. Only 4 participants are there, including me. Just inform all your friends to join. Students, kindly rename your name with register number followed by your name. Students, kindly rename with your register number followed by your name. If you didn't rename your name, you will be removed from the meeting, ma. So kindly rename it and we will start the class soon. Only less participants are there. Yes. Good evening, students. So I hope you are going to appear for your university examination. So you are being prepared for the examination. So today I'm going to cover the first unit and some of the important problems in that. So I will share the screen for you. Okay. So magnetic circuits. You all know that you have been seen with the magnetic circuits. Able to see. So listen, why I'm sharing this screen now. You kindly note down the formula. First unit is, we all know it's about electric circuit and magnetic circuit. We are seeing the relation between the electric and magnetic circuit. And in this particular unit, you have only two important questions as a theory part. The comparison of electric and magnetic circuit. And another question is from the uh, types of induced EMF, and you have to explain about what are the types, and you have to obtain the expression for self-induced EMF, mutually induced EMF, and one more important thing is about the expression, the relation between the self and mutual induced EMF. Okay, so now you take down this particular formula relating the problems from the magnetic circuit. One of the very important thing. So flux, now we have always two formula, magnetic flux density into area or MMF by reluctance. We all know that once again. So flux, you take down this formula, flux is nothing but flux density in the area. And another formula is flux equal to MMF by reluctance. We all know what is flux, total number of magnetic lines. So we can find out two-way for the flux value, and the unit is in Weber. Okay. And the next one is magnetomotive force, MMF. MMF, we can easily relate with the electric circuit, V equal to IR. Similarly, MMF, V na, it's nothing but voltage, EMF. Electromotive force equal to voltage is nothing equal to current into resistance. Here, the same way, we can relate that MMF equal to flux into reluctance. That is this is MMF equal to phi into S. This is one of the very important formula. I think I'm showing the this is one of the very important formula. MMF equal to flux into, this is nothing but V equal to IR formula. V equal to IR. Okay. And then reluctance formula. We can easily compare the reluctance with the resistance. R equal to rho L by A. Just kindly highlighted whatever the formulas I have highlighted in yellow color. You kindly write it, because we are going to solve the problem based on that. Okay. So magnetic flux, it's nothing but current. Okay. And magnetomotive force is nothing but EMF. Reluctance is nothing but resistance. So R equal to L by nu A. Nu is nothing but nu naught into nu R. Magnetic flux density, B is equal to phi by A. Magnetic field strength, we have two formula for this. B equal to nu H, you have already studied B equal to nu H. And another formula is H equal to Ni by L. Okay, so please kindly note down all these formulas, which is highlighted in yellow color. Actually, I will rub it. You need not to get confused on that. Okay, you just take down this formula, which is very, very important for solving the circuits, whether it may be a part B or part A, whatever may be your circuit, it will be very important. Yes, I have mentioned the unit also. Yes, you just kindly note down all the formulas. Okay. See, students, you don't record that, because whatever we were been taking the class, we have been sharing in YouTube. So the YouTube link will be shared to you. So no need of asking any recording permission from your side. It's clear? We will share this entire thing. Okay, I hope you have written the formulas. Okay, and the next one, another important formula, take down the leakage factor formula. Total flux produced by useful flux. Take down that formula. Okay, leakage factor is equal to total flux produced by useful flux. Okay. And okay, this is one important question we have mentioned. The difference between electric and magnetic current. Just one recall. Magnetic flux is flow on the closed path. Now it is magnetic circuit. Electric current is flows on the closed path. Now it's electric circuit. We were telling magnetic flux in Webers, na electric current in ampere. Magnetomotive force na N into I we are measuring. Electromotive force V equal to IR. Okay. Or else we can say magnetic motive force in another way, flux into reluctance, because Flux is equivalent to current. Resistance is equal to reluctance. And these are the formula. We are comparing the reluctance. Permeance. Permeance means reciprocal of reluctance. Reluctance, now you have to understand that the property of resistance is oppose the flow of current. The property of reluctance is oppose the flow of flux. Okay, so I think these are the important comparison. This is one of the important question. Okay, this is one part B. Theoretical wise, you can expect this analogy of magnetic and electric circuit. Nearly some 15 points have been given. So try to write all these 15 points. Okay, and the next important theory question is this question. Explain the types of induced EMF in detail. Now, we have two types, dynamically induced EMF, statically induced EMF. Statically, we have two types, self-induced EMF and mutually induced EMF. So, if the question has not been specific, you have to explain about both dynamic and static. If the question is so specific to explain about dynamically induced EMF, you have to derive the formula E equal to BLV sin theta. Okay. And statically induced EMF, we have two types, self-induced and mutually induced EMF. Okay. This is another important part B question, theoretical question. Types of induced EMF. Now, you have to explain all this statically, dynamically. Statically, again, we have two expression, self-induced EMF and mutually induced EMF. Okay. I think this all been covered, and you see, I think I will write it here. Okay, E equal to BLV sin theta. Okay, flux density, length, velocity, and here we have a two type, L equal to N phi by I. That is self-inductance value. Self-induced EMF na E equal to L di by dt. Due to rate of change of current in same coil, and EMF is induced na self-induced. Mutually induced EMF na due to rate of change of current in neighboring or vicinity of the coil, and EMF is induced na, that is mutually induced EMF. So M, we all have, we know flux linkages per unit current in the other coil. N151 by I2 or N252 by I1. Okay, so this is another important part B. Don't forget to study these two questions. Both are very important. And we all know the relation between the self-induced EMF and mutually induced EMF. Okay. So you take down the next part B question is from the first unit is. So you have only two part B question. The rest of the things are only the problems. Okay, I think I will show you one more important, I think this are K equal to M by root of L1, L2. This particular slide. This particular slide, you take down dynamically induced EMF E equal to BLV sin theta, self-induced EMF E equal to N d phi by dt. It's nothing but Faraday's law. And mutually induced EMF M di1 by dt and L di by dt, all we can write. First, this is mutually induced EMF and this is self-induced EMF. Okay, and both will be comes under statically induced EMF. And the formula for self-inductance and the formula for mutual inductance and coefficient of coupling. Okay, so this is another, already I have shown the formula for electric circuit, and this is the another formula for magnetic electromagnetic induction. Both are very important for solving problem as well as for your derivation. It will help you. Okay, now I will okay, students, I think I hope you have been seeing the questions. Okay. Now you kindly take down this particular question. An iron ring of mean length 50 centimeter has an air gap of 1 mm. I have highlighted there now. You kindly we will see some important part B problems in the question. I think before that, I will show you. You see, illustrate the relation between reluctance and permeance. We all know that the reluctance and permeance. Reluctance is nothing but oppose the flow of current, flux, and permeance reciprocal of reluctance. Retentivity, I think in BH curve, we will see that how it gain its magnetic property and all explained by the term retentivity. Fringing effect. So fringing effect means while we are seeing that while my flux passes through the air gap, it will be bulged towards the end of the air gap. So at that time, the area of cross section get increases. So flux density get decreases. That is the effect. Ohm's law of magnetism. Ohm's law of magnetism. V equal to IR. It's in Ohm's law for electric circuit. And Ohm's law for magnetism is nothing but MMF equal to flux into reluctance. And see, these are very small problems. Okay. Iron ring, this and all we will see. You may use it and try to get the answer. A bar of iron 1 centimeter square, cross section has 10 power minus 4 Weber of flux in it. Find the flux density in the core. Okay, first I think we will see the part B problem, then we come to the part A problem. The rest of the thing, Faraday's law of electromagnetic, Lenz's law, statically and dynamically. Statically induced EMF na best example is transformer. Dynamically induced EMF na best example is when you go with that, the best example we used to say that generator. Okay. And describe leakage flux and the leakage factor. Illustrate Fleming's left-hand rule and right-hand rule. Okay, Fleming right-hand rule for generator, left-hand rule for motor and all. That all we have to study as a 2 mark. This is, but when you go with part B, you see, I told there are probability questions are very less here. See, derive the expression for self-inductance, mutual inductance, coefficient of coupling. All this are comes under statically induced EMF. Then the second question is explain Faraday's law of electromagnetic induction. Derive the expression for dynamically induced EMF. That is, we have to derive all the Faraday's law. Explain the Faraday's law now. The Faraday's law means we have to produce the rate of change of flux, and due to rate of change of flux, an EMF has to be induced. So that we have to say, and we have to derive the expression. And then statically induced EMF. You have to, both 1 and 3 are same question only. Okay, actually I told you that don't ask for recording. We were been sharing in the YouTube. So YouTube link will be shared to you for this particular session. Okay, and then we have some problems. The last one is, see, discuss the similarity and dissimilarities of electric and magnetic circuit. And with a neat sketch, explain series and parallel magnetic circuit. So series and parallel magnetic circuit, I will explain you. So now I will show you the now I will show you the problem and we will solve this problem. Okay. Okay, take down this problem. This is the problem I gave you. Yes. Solve for this problem. Okay. Okay. An iron ring of mean length 50 centimeter has an air gap of 1 mm and winding of 200 turns. If the permeability of iron ring is 400, when a current of 1.25 ampere flows through the coil, find the flux density. Okay. So in this particular problem, you start solving, and now I will allow you to put it in the chat. Okay. An iron ring. Okay. In this iron ring, okay, the length of the iron ring is 50 centimeter. And you have seen a small air gap is also there. So you cut the provision for the air gap. This is a air gap. Okay. And total number of turns is 200 turns. Okay. And permeability, nu R value is nothing but 400. And current is 1.25. I have to find out the flux density value. Find the flux density value. Yes. How we can solve this problem? Yes, how we can solve the problem? Find the flux density. Okay. So we all know flux density, we have two formula. What are the formula? B is equal to flux by area. Okay. But we all know that the flux value, and another formula is B is equal to nu H. These two formulas are used to find out the flux density value. So first we find out the total MMF. Okay. From what is the formula for MMF? MMF, what is the formula? We have a flux into reluctance formulas are there. Okay. So phi into S. We can put, or MMF equal to N into I. Okay. And first you find out the total MMF. For total MMF you find out total MMF N into I. What is my N value? Number of turns is 200. Okay, 200 turns and current value is 1.25. So what is the flux density? Put it over the chart. Yeah, 250. Okay. So total MMF, what is the unit for MMF? What is the unit for MMF? MMF, what is the unit? Ampere turns. Good. Ampere turns 80. Okay. So we have find out the total MMF value. But we don't know the flux value. Okay. So we are supposed to find out the flux value. Okay. Because we are need to find the flux density value. So flux value we have to find out. So how will you find out flux? It is a, it looks like a series magnetic circuit. Series magnetic circuit now. Yeah, I will draw you. Series magnet now phi equal to, okay. In this, we have to see that flux in the entire circuit will be same. In series, flux is same. Okay. So to find that, we are finding MMF, total MMF. We all know the value is 250 ampere turns. So you keep that 250 in one side. Okay. Flux into reluctance. We have a two types of reluctance. One is in iron core and another one is in air gap. So S ion means, or S1 you can take. Iron core and another one is in air gap. So SG. What is the formula for reluctance? What is the formula? L by nu naught nu R into area. Similarly, Lg by nu naught nu R into area. My mic is unmuted. Muted. You can't able to hear my voice? Kindly anyone acknowledge? Kindly audible only. Yeah, you check your audio system. Thank you. Vivo and all, you have to rename with your register name. I already told you. Okay. Okay. Now you substitute all the values and find out flux into L, length of the air gap. So you see total length, a mean length is 50 centimeter. Okay. So has an air gap of 1 mm and winding of 200 centimeter. So you have to understand that a mean length, iron ring having a mean length of 50 centimeter. Now, L is nothing but L equal to Li plus Lg. I think the difference will be very less only. Okay. So the mean length is what? 50 centimeter. So 50 into 10 power minus 2. We have to substitute everything in mean value only. Sorry, SI unit only. Li value. Okay. This is you have to know. So substitute Li value. What is nu naught value? Did you remember nu naught value? 4 pi into 10 power minus 7. Yeah. Nu R value is 400. Okay. And area they didn't mention about area, so I think we will take area is also unknown, 5 by a. Okay, 5 by a, we can take it outside because the fringing effect here we are not considering. So fringing effect is not considered. Now both the area will be same. Lg means what? Length of air gap, that is 1 mm, 1 into 10 power minus 3. Okay. And 4 by pi into 10 power minus 7, and nu r value is what? Into 1. Okay. So 250 is equal to flux by area. This is B, and find out all this value and divided by that will give the B value. You substitute and you find out. Can you understand what I'm telling? Anything over the chat, you kindly reply me, ask any doubts. Can you understand? It is one of the question we have shown you, the series magnetic circuit. Series electric circuit, na, very simple. Both the resistance will be, we have to add. Similarly, here also, it are resistance, na, here it is reluctance. So we are adding the reluctance of the iron path plus reluctance of the air gap. Okay. Have anyone find out the flux density value? Have anyone find out, ma'am, last step, can you explain it? Yeah. Actually, you all understand. Li by nu naught nu r. Reluctance formula we know. L by nu naught nu r into A. That's why in the first slide, I have shown some of the formula. What? Very simple formula. Flux density equal to flux by area. MMF equal to flux into reluctance. B is equal to nu H. H is equal to Ni by L. Some 10 formulas are that you have to remember. So here, we have find out the Ni value. Okay. And A, both the cases, yeah. Why I am saying both the areas are same now? You have to understand this area and this area are so same area of cross section. That's why I have taken both the area, A as a common. So L by nu naught nu r plus Lg by nu naught nu r. Nu naught is nothing but absolute permeability. Absolute permeability, the value of nu naught is 4 pi into 10 power minus 7. And nu r is relative permeability. In air, the relative permeability is always 1. But when you go for any iron material, the nu r value is around 400. Okay, so that's why we substitute. Here, they are given in the problem, nu r is 400, or else I have to take it along with that only. Okay, so I have to take my nu r value as a 400. You see, this is the 400, they were given the value. And now, can anyone, have you find out the values? Just kindly note down the answer, you may check it. Okay, actually the final answer is 94.2 milliweber per meter square. Anyone getting? Kindly note down. The answer is 94.2 milliweber per meter square. So we have find out now reluctance of the air gap plus reluctance of the air gap plus reluctance of the R1 plus R2. Now one is about the air gap and another one is about the length. Here they didn't subtracted, but normally when you subtracted L equal to, I told you now, Li plus Lg, you just remember it is a 50 centimeter minus 1 mm, the value is very less. But even when you subtracted, you will get more accurate. Okay, but even you subtract, that is the general procedure. But the flux density, are you all getting this answer? 94.2 milliweber per meter square. Ninety-four point two milliweber per meter square. Have you all getting? Yes or no? Yes, ma'am. Okay. Okay. Okay, ma. Okay. So now I think we have solved one part B question. I will take one part A questions from this because we have already seen with this. Can anyone tell me the formula quickly? This is one part B question. We will solve a bar of iron 1 centimeter square cross section. This particular problem I have highlighted. Okay, what is the magnetic field intensity formula? Tell me what is the magnetic field intensity formula? H is equal to Ni by L I can use. Okay, Ni by L. But again, when I go with that number of turns, current is not given. So I have to definitely use what formula? B is equal to nu H. B is equal to nu H. So first you find out the value of B. What is the formula I have to use for B? B is equal to what? One formula, flux by area. Flux by area, na, flux is in 10 power minus 4 Webers divided by 1 centimeter square. So 1 into 10 power minus 4. So I think what is my flux density value? What is the flux density value for the fifth problem? Fifth part A question. It is part A question. See, very simple thing. Same repeated problem only we have been using. Why we are not using H equal to Ni by L? Na? You have to understand that. Yeah, Rahul Subramanian, correct. B is equal to flux density is equal to 1. 1 Weber per meter square. Okay, find out the value of H. Find out the value of H value. Magnetic field intensity, I have to use what formula? B equal to nu H. B equal to nu H. Now, you have to understand Y equal to nu naught into nu R into H. Nu naught value we all know 4 pi into 10 power minus 7. And nu R value 2000. The relative permeability will change up according to material. Some of the problem they didn't given na, you can take it that is a air core inductor and you can take it that value as a 1. What is the H value? Tell me. What is the H value? B is 1, correct, Akash, correct. What is the H value? Calculate the H value for this case. Calculate the H value and tell me. Yes. Have you see? One of the most important is whatever you are doing, don't do with your mobile. Have a practice in the calculator because in the examination, calculator is only allowed. So especially the first unit, have a problem. So that's why we have been teaching from first unit onwards. 398.63. What is the unit? It's correct. 398.63 H value. H is equal to 398.63. Anyone getting the same answer? Kindly acknowledge for the answer. Magnetic field intensity in the bar. Ampere turns per meter. That is the unit for H. Always mentioning with unit is very important. Yeah, very good, Akash. 398.08. That's not a problem. The fractional value got a difference now. It's not a problem. So 398.0308 ampere turns per meter. That is the correct answer. Okay. So this is one part B, important probably. Then do the sixth problem. Do the sixth problem. Do the sixth problem. So here, very simple, my B value is 1 Weber per meter square and my H value is nothing but 398, okay, 398 ampere turns per meter. Okay. Then do the sixth problem. A solenoid wound with a coil of 200 turns carrying a current. I think it's a direct formula. H is equal to Ni by L. H is equal to Ni by L. Okay, so 200 turns, N is 200, current is 1.5, length is in centimeter. Convert into meter and find out the H value. Find out the H value. Sixth problem. It's all 2 marks. So that's why I told the first I have shown you the important formulas. H equal to Ni by L. Yes, kindly tell me the answer for this. Yeah, I am getting the answer. Yeah, Devadarshini. 375 ampere turns per meter. Yes, Akash also. 375 ampere turns per meter. Good. Others, you are supposed to solve. Okay. Yes, ma. Yes, Mukesh, correct. 375 ampere turns per meter. 375 ampere turns per meter. Direct substitution. No need of confuse over this. H value is again 375 ampere turns per meter. Okay. Tell me the seventh problem. Seventh problem, what formula we have to apply? Air core solenoid 400 turns, length is given, cross-sectional area is given, self-inductance, whatever we are solving are very important one. Air core inductor. Actually, self-inductance, we have a 2 formula. L equal to N5 by I. That is flux linkages per unit current. But by seeing the given data, flux is not given and all. So I have to go with what formula? Na? L equal to N square by S. I have to go with the second formula. L equal to N square by S. So N square by S, na, S is again reluctance. L by nu naught into nu R into area. Okay. So seventh, even see students, you have written the formula correctly. Some of the time your calculation is wrong. By formulas are correct now, at least you may get a minimum of 1 marks because it's a 2 mark question. So remember that mind, you write the value correctly and put the formula correctly, mention the unit correctly, then only you will get full mark. Okay. So L equal to N square by S. Use that formula. Air core inductor they have given. You see, air core inductor na, we all know that my nu R value is 1. Okay, so L equal to N square. That is my 400 turns divided by L by nu naught into nu R into area. Okay, Length is 30 centimeter. Convert into SI unit. 30 centimeter, 30 into 10 power minus 2. Area 5 into 10 power minus 4 meter square. Have anyone find out the self-inductance? This is the formula I have to use. L equal to N square by S. For S, L by nu naught nu R area. So nu R will be 1. I told air core inductor means they have given. Yes, solve for that problem. Wait. Okay. Can anyone tell the answers for this particular problem? N 400 turns. Length of the coil is 30 into 10 power minus 2 meter. Area will be 5 into 10 power minus 4 meter square. And the relative permeability nu R will be 1. And then when you go with that, 477. What is the unit for self-inductance? What is the unit for self-inductance? What is the unit for self-inductance? Why there is no answer? Unit for self-inductance? Henry, yeah. 477 are all Henry, HENRY, the inventor name. Darshan, what's your doubt? Why you raise your hand? You're checking whether all your tools are working properly. Yes, I hope everyone will get that value. 477 Henry. Okay. Whether you got that value? Okay. And tell me the eighth problem. Eighth problem. You kindly tell me the eighth problem. A current of 2 ampere passes through a coil 350 turns wound on an iron ring of mean diameter 12 centimeter. The flux density in the established ring is 1.4 Weber per meter square. Determine the relative permeability of the material. Okay, actually, we all know this particular formula. How we were been finding now? MMF equal to flux into reluctance. Okay, flux we all know what is the formula? N into I. Okay, and here they have mentioned about flux density. Flux density na 5. Reluctance value, what is the reluctance value? L by nu naught nu R into area. So instead of flux by area, I can put what? B. Ni equal to B L by nu naught nu R. Okay, I think all the data we know. N we know, I we know, B we know, L length is we know, and nu naught values we know. So find out only nu R value quickly. Tell me the value of nu R. In this particular thing, Ni. See, I am writing from the basic formula. MMF equal to flux into reluctance. And reluctance is nothing but length by L by nu naught nu RA. So when I am substituting my value, tell me the value. 350 turns. 350 into current is 2. Flux density. That is given 1.54 Weber per meter square. Mean diameter. Okay, mean diameter now, we all know how to find out the length of the coil. We are known a radius now, L equal to what I have to put? 2 pi R. R I can use pi into D. Okay, I have to use. They have given the diameter. From that, I can find out the length. Find out the nu r value. Length is nothing but pi into d. I am substituting pi into d. And nu naught, 4 pi into 10 power minus 7. And only unknown value is nu r. Tell me the nu r value. Tell me the nu r value. Anyone finding the nu r value? Once again. Yes, some of them are find out. 2.90. You all understand, while you're getting the value itself, you have to know whether your calculation is correct or not. Air core inductor only one. So when you go with that, it will be around some 500 or 200. That is the value only we are keep on seeing. It's a some 3-digit value only. So newer will not be 599, no unit. Very good. Newer, it's Akash, it's correct. 599, it doesn't have a unit. Newer value is 599. Yes. So take down. Yes. And one more thing. One more problem, I think so. So newer value is 599. I think here only some students were been repeatedly giving the answers. This is easily scoring subject, not a tough subject. Okay. Okay. The next ninth problem alone, you tell me. Ninth problem. Again, it's a 2 mark. EMF induced in the coil. Okay. We all know E is equal to N d phi by dt. Okay. N is 200. Rate of change of flux. 3 milliweber to 1 milliweber, or 1 milliweber to 3 milliweber. No? 1 minus 3 milliweber minus 1 milliweber divided by 0.1 second. Okay, what is the induced EMF? 600. Yeah. Okay. So ninth problem is very easiest problem. Calculate the EMF induced in a coil. E equal to N d phi by dt. Okay. You substitute and tell me what is the answer. I think around 4 volt we will get it. Okay, induced. The ninth problem is around 4 volt. Okay, so I think here we have seen about the part A question and part B. In the part B, okay, take down the formula for ninth problem. E equal to N d phi by dt, and the answer is 4 volt. Okay. So the rest of the thing which is shared to you, okay, part B, we have a, I think I will tell you the fifth question alone. Okay. Sixth question, you just note down the sixth question. You try the sixth question. Okay. I'll solve the fifth question and the next sir will continue. Sir, have you joined, sir? Sir is joined. So I think you take down the sixth question. I will explain you the fifth question alone. Okay. Have you all take down? I think not a big issue. This link will be shared to you. So you may see it in your free time. Okay. Yeah. This is the question, ma. An iron ring take down an iron ring 8 centimeter diameter. Okay, take down this question. Okay, so I will draw this. An iron ring of 8 centimeter diameter is made up of round iron of diameter 1 centimeter and permeability 9. I think it's almost similar to that problem. Okay, so you just see this. This is my ring. Okay, in this ring, it is, if they ask about series magnetic circuit, you randomly draw this and you explain parallel magnetic circuit. I think the faculty member have been teach in the class, taught in your class. Okay, now again I'm saying MMF. MMF now we all know what is the formula, Ni. Okay, N into I. Resistance now we all know that is not resistance, reluctance. Si plus Sg. Okay, so while I am finding my total MMF value, that is N into I. Okay, 3.5 ampere and 9, what is the number of turns? 400 turns is given. So 400 into 3.5. Total reluctance, Si plus Sg. Total reluctance, na, Si value is nothing but what will be the value we will write? Li plus Li by nu naught nu r into area. Lg plus nu naught nu r into area. Okay. And here they didn't mention about fringing. So we have to take both the areas are same area. So you see here diameter is given 8 centimeter. Now radius will become 4 centimeter. It's nothing but a 0.04 meter. Okay. And when you go with the air gap length, it is nothing but 2 mm. Air gap length is 2 mm wide. Okay, mean diameter is 8 centimeter mean diameter. So if I want to find out, I can say that L equal to, I can use what formula? Pi d. Okay, and while you go with that, diameter of the round, that is, this diameter is given 1 centimeter. This diameter is 1 centimeter. Can you understand the difference between this diameter and this diameter? This is mean diameter. Can you understand? This is mean diameter and this is round. So if its diameter is given, we all know we can use how to find out the area, pi r square. Find out the total reluctance. And when you go with that, MMF, if I know, reluctance I know, flux is very easy. Flux is now, MMF is equal to flux into reluctance. So MMF by reluctance gives what? My flux value. Flux density na flux by again area. Okay. So I think these 4 formulas only we were being using. Okay. Okay, take down the answers alone. You check it. Okay, ampere turns is 1400 ampere turns. Total reluctance is 0.103 ampere turns per Weber. And flux value and flux density value. You check it whether you are getting the same answers. Okay. And that leakage coefficient formula also you may try it. Yes, all the best. First unit, I think I have been sharing that again. Okay, prepare well for the exam. Sir?
Good evening, ma'am.
Good evening, sir. Good evening, sir. I think first unit, except one problem, I have given the answers as well as the procedure. You may take over the session, sir.
Thank you, ma'am. Thank you.
And thank you, sir. Thank you, students.
Good evening, students. Am I audible? Okay, thank you. Okay, I'm going to deal the second unit. Second unit, we are going to deal about the DC generators. About the DC generator, we are going to discuss. In this, main topics are construction and principal operation of the generator. This is very, very important question. Okay. And then EMF equation. EMF equation, problem and theory, they may ask. Okay. And then types of generators. These three questions are very, very important in the second unit, the DC generator. Initially, I will teach the introduction about the generator. Then I'll teach you these three main topics. Then I'll teach you the important questions, 2 mark and big question. Is that okay? Anything if it, please message me in the chat box. Otherwise, anything if you record, you tell me, I'll teach you first. Okay, thank you. So first, you all know that generator is nothing but it is going to convert mechanical energy into electrical energy. Okay, so it required a mechanical energy as input, and the mechanical energy, input energy, is converted into electrical energy. Okay, so the electrical energy is the form of DC. Electrical supply have two quantity. One is direct current DC and alternating current AC. Okay, so here we are dealing about the DC generator. So the output should be a DC. Okay, so the DC generator means it is taking input as a mechanical energy and it is going to provide electrical energy, DC supply. DC power is given as output. This is what generator. Okay. I'll make your slide. So, okay. Right. Next. So this is what is given here, right? So it is working on the principle of Faraday's law of electromagnetic induction principle. Okay, Faraday's law of electromagnetic induction principle, it is going to operate it. It is going to produce a voltage, EMF, right? So there will be two types of EMF we discussed in first unit. Anybody can please tell me what are the type of EMF we discussed in the unit 1 in the chat box? There is a two types of induced EMF we discussed in unit 1. What are the type of induced EMF we discussed? Very good, Bharat, right? Good, Remy, good. Okay, Remy also joined. Okay, good. Statically induced EMF, dynamically induced EMF. That's the two types. First, you need to know what is statically induced EMF, what is dynamically induced EMF. That law and all you would have studied in the unit 1, magnetic circuit you would have studied. Okay, statically induced EMF, keep in your mind that conductor is stationary. Okay, conductor is stationary, magnetic field is varying, rotating, then it is called statically induced EMF. And second one, dynamically induced EMF. Conductor is rotating, magnetic field is stationary, constant. Then it is dynamically induced EMF. So the DC generator comes under the dynamically induced EMF. Okay. So the transformer comes under your statically induced EMF. Okay. Fourth unit you will study as a transformer. So it's dynamically induced EMF, conductor is rotating, magnetic field is stationary. The rotating conductor, it cuts the flux. There's a rate of change of flux. So EMF is induced. Then it is called dynamically induced EMF. Clear? I hope you all understand how EMF is going to generated in the DC generator. So DC generator, conductor is rotating, magnetic field is stationary. Okay. Here, next slide. I'm moving to the next slide. Okay, now we are coming to here, right? This is what the principle of operation. But better understanding, they were given here actually. North and South pole, it's given here, right? I'll animate and I'll take wait. So this is what your magnet, okay? North pole and South pole. This is nothing but stationary magnetic field as we have discussed. Okay. So magnetic field is here. Here the magnetic field is available. It is moving from the North pole to South pole. It is moving, right? Now, it's a rotating conductor. Single conductor I have taken as an example. As a single conductor, it is rotating in the magnetic field. It's a conductor, see square shaped conductor, sorry, rectangular shaped conductor. It is rotating in the magnetic field, right? This rotating conductor produce induced EMF. Okay, this is what the dynamically induced EMF. You know the Faraday's law, whenever conductor cuts the flux, there is an induced EMF in the conductor. Okay, so right. So on the next slide, this is what the principle of operation. Okay, I'll erase it. Okay, right. So the next slide, as we have discussion from the Faraday's law of automatic induction, EMF induced in the conductor E is equal to N into dy by dt. Here N is equal to 1, E is equal to N into dy by dt. So as per the first unit, as I had discussed, dynamically induced EMF derivation, E is equal to BLV, right? B is nothing but flux density, which is created from the magnet. L is nothing but length of the conductor. V is nothing but velocity. Right. So this is what the thing actually. So now when the conductor is moving, see, now the conductor is, both are right angles to each other. Magnetic field and conductor right angles to each other. Okay. So first position you can see cut magnet flux cutting that will be given based on the how much EMF is induced, how the EMF is induced based on the angle it is given. 0 degree when the conductor is in 0 degree, when the conductor is less than 90 degree, when the conductor is 90 degree. Based on that, how much EMF is induced? That is given flux linkage. Based on the flux linkage, the EMF will be varied. That is given here, right? So this is called an induced EMF. As per the Faraday's law, induced EMF is AC. It is not DC. So we need to convert, but it's a DC generator. We need to convert the AC into DC. We'll be using a commutator. Commutator as an element we'll be using. I hope you understand what is generator, what is the principal operation of the generator. You understand. Now I'm moving to the construction of the generator. Okay, so if they asked construction of the generator or DC motor or DC generator, you need to draw this diagram. This is very, very important. So evaluator, they'll be checking that first whether you have drawn this diagram or not. This diagram will indicate you all the parts of the DC machine, generator or maybe a motor. Okay, so what are the main parts of the DC generator? Is yoke. The first part is nothing but yoke. Okay. So this is what first part yoke, right? It is nothing but outermost cover of the machine, right? It is made of our cast iron, cast steel material. Okay, it is going to protect inner parts of the machine. Okay, and then it is provide flux path. It is provide a flux path. Okay, so these are the points you need to write. This is important points actually. Here, what it is made of. What is the function of that? That you have to write for each part. The first part is nothing but yoke. Okay, it's the outermost part of the machine, made up of cast and cast steel material. Okay, and then it is going to provide protective cover for the inner parts of the machine, and is going to provide a path for the flux. Where the flux is produced? The flux is produced in the stator. There is the two main parts of the machine, stator and rotor. Stator is nothing but field. Rotor is nothing but armature. Okay. In the stator, now next we are going to discuss about the stator. Stator is nothing but stationary part of the machine. Rotor is nothing but a rotating part of the machine. Okay. Next, the stator, we have pole core, pole shoe, field winding. Three main parts are available. Pole core, pole shoe, field winding. Here, this is nothing but your pole core. Okay, this is your pole core, right? And this is your pole shoe. This is what I'm writing. This is nothing but pole shoe. And this is nothing but field winding. It is wounded in the core, right? Pole core, pole shoe, field winding. Okay. So it is also made up of cast and cast steel material. Okay. And then pole core and pole shoe, I'm saying, right? So pole core and pole shoe made up of cast and cast steel material. The pole core, which will be connected to the yoke with help of the bolt and nut, mechanically supported with help of the bolt and nut in the yoke only, right? This is a part where the windings are wounded on that. Field winding is wounded on that. The pole core only, the field windings are wounded on that. Okay. And then pole shoe. Pole's main function of the pole shoe, it is going to spread out the flux uniformly in the air gap. Air gap is nothing but this is what your air gap. Whatever the rotor is available, no, that part is nothing but air gap. We want to try to say, right? So it is spread out the flux uniformly in the air gap. That is a function of the pole shoe, right? And the field winding, it is made of a copper aluminum material, right? So when current pass through the field winding, it is produce the flux. And the current pass through the field winding, right? So it produces a flux. So constant flux is created here. As our discussion, flux is stationary, conductor is rotating, right? So constant flux it's be created with the help of the stator, field winding, field. With the help of that, constant field is created here. Okay, field is constant. It's not varying one. It is created with the help of the stator, right? I hope you all clear, right? Any doubt, you can put a chat box. And then rotor. I'm coming to the rotor side. The rotor, it is in cylindrical in shape, right? There is a slots are there, outer periphery of this your core, armature core. Inside the slot only we are keeping conductor. So I wanted to say here, right? I'll take red. That will be good. Huh? So this is your armature. This is armature core. Outer periphery, there is a inward projected. Say this is called inward projected. What I'm saying, inward projected slots are there. Inside the slot, the dot mark which is given, that is nothing but conductor. Right? There's a conductor we'll be keeping. The conductors are connected in a two types of winding: lap winding, wave winding. Two types of winding it was made. It's a comparison we'll discuss later. So this is what armature slots are there, and armature conductors are inside. The armature conductors are connected in lap or wave winding, connected in such a way that, okay, it based on that customer requirement. How much you want a high voltage if you record, or if you want a high current you record, based on that it will be connected. Okay, and then the armature cores are laminated in construction. This was asked in the CAE question paper also, to reduce the eddy current. To reduce the eddy current, it has been laminated, and silicon steel materials is used to reduce the hysteresis losses. To reduce the, so what is hysteresis loss? What is eddy current loss? Already we have taken in the class more classes. right? Hurry up, we will go on very faster, right? Still, we need to start more things, right? And if anything record, you put it in the chat box. At end of the class, we'll teach you about that. And then, so here we need to provide a prime mover, right? Because as we are told, right? So we record mechanical energy as an input. So we are providing mechanical energy input to the rotor of the machine, so that it will get start to rotate it as a prime mover is connected. A prime mover may be a motor, same motor, or maybe IC engine, petrol engine, whatever maybe, it will be connected, right? It will be rotating, so that rotor is rotating, rotor conductors or armature conductors are rotating. Clear? This rotating armature conductor, it cuts a flux, so that EMF is induced. Clear? Right? Next part is nothing but commutator. So this part, this is nothing but a commutator as our discussion, right? So commutator is nothing but it is also rotating part of the machine. Number of, because a commutator is nothing but number of commutator segments are available. See here, some segments it's given as like a segments, right? Number of commutator segments are there. Number of commutator segment is equal to number of armature coil. How many number of armature coils are there? That many number of commutator segments are available, right? So each commutator segment is connected to the armature coil. So induced voltage in armature coil is AC. That should be converted into DC with the help of the commutator. Each commutator segment is connected to armature coil, one single armature coil. So induced EMF is AC. That AC voltage is converted into DC with the help of the commutator. That is what the function of the commutator actually, right? And carbon brush. So through your carbon brush assembly, the produced DC voltage is given to your terminal box. Output of the terminal box, it has been given. Okay. So this is what the construction of the DC generator. This is very, very important question. Right. So next I'm moving. Okay, this is what I'm discussed. This is only available here, right? Field winding, ball shoe, and armature core, armature winding. Okay. Commutator and brushes. These are things are available. Next, we want to discuss about the comparison of the lap and wave winding. So where you can use a lap winding, where you can use a wave winding, right? So this is important 2-mark question will be asked. Number of parallel path is equal to number of poles. Number of poles is equal to number of parallel path. Number of parallel paths is equal to 2 for the wave winding. And then number of brush sets required equal to the number of poles. Number of brush sets required always equal to 2. Preferably lap winding it is used for high current. It is for high voltage. That is only you keep in your mind. High current lap winding, just to keep in only one point. Keep other thing you can able to write. Don't mug up everything is right. So this is what the comparison of the lap and wave winding. Okay, and EMF equation. This is very, very important question. EMF equation also. So how much EMF is going to induce in the generator that we are going to discuss here. I hope it's a derivation. You can able to do this, right? So now we'll solve the problem related to that. And then, okay, this is very, very important question. This we'll discuss. So EMF equation derivation, you can able to derive that, right? Generator construction is discussed, principal operation is discussed, and then now we are going to discuss about the types of the generator. What are the method of excitation is available? This is very, very important question actually. There will be 2 types of excitations are available. Separately excited, self-excited. Okay. Separately excited, self-excited. Okay. See, first you see this diagram, separately excited. See, this diagram you see, separately excited generator. Here the field winding. Excitation is nothing but how the field winding is energized. How the field winding is energized. So based on that, only excitation is discussed. Here the field winding F1, F2, it is energized separate DC source. See here, separate DC source is connected here. Okay, so it is called separately excited DC generator. That means that other than the mechanical energy input, so mechanical energy input is given here, right? It will be given to your armature, but mechanical energy is given. Other than the mechanical energy input, so there is an DC supply which is given to the field winding. Separately, DC supply is given. Okay, so it is called separately excited DC generator. So you understand and study, don't muck up. And self-excited, what is the meaning of self-excited? See, here the DC supply is not given to the field winding. See, the field winding DC supply is not given. It is connected to the parallel with the armature. So it is called shunt generator. Here the field winding is, see, this field winding is connected in parallel. So shunt generator. Here the field winding is connected in series with armature, series generator. Okay. So you understand and study. Here the field winding is not energized with the help of the separate DC source. Energized by themselves. That means that there is a flux which will be available in the field winding itself due to the previous usage. That's called retentivity that you have studied in magnetic circuit. So this residual flux will produce some voltage in the armature winding. So some flux is available. So now mechanical energy is given. So armature conductor cuts a small flux. The small flux it cuts, so small voltage get induced. So that voltage will pass the current in the field winding. At the same time, we give the current to the load. So now the small flux build up. Say an example, it's the range of 0.5 ampere initially. Now 1 ampere, 1.5 ampere. Like that, it is keep on build up. So we are not at all providing external DC supply to energizing of the field winding. It's called self-excited. All the things like that only. Compound. Compound is nothing but combination of shunt and series. It's a combination of shunt and series. It's called compound. Okay, right? I hope you understand what is separately excited generator, what is self-excited generator. Right? One by one we'll discuss. This is very, very important question. Please listen carefully. Okay, separately excited. This is what the diagram. You need to draw this diagram. Then you need to write the equation. How to write an equation? So we write an equation for generated EMF equation you have to write. So in this diagram you see, here load, this is the load which is connected in the armature. So this is called IL, load current. Armature current which is generated, it's called IA. So IA, IL both are same. So you need to write first IA is equal to IL. Clear? Next you need to write this equation, like write an EMF equation. See here, and one more thing here, the EMF also generated, that also you need to write EG. That is only you want to write. So it's written this side, but it's not mentioned, right? EG, this only I wanted to find out. Okay. So here the load voltage, we can assume that as a V. So you apply a KVL equation on that, right? Apply a KVL equation on that. So that you will get V plus IL into RA. RA is nothing but armature resistance. So this can be written EG is equal to EMF induced in the armature EG is equal to V load voltage. Sometimes they may say VL, V plus IA or IL, both are same, into RA, right? I hope you understand how to write an equation. This is for separately excited. Clear? So similar way you can write equation. Any doubt on this? How to write a equation? Okay. Next, this is separately. So you have to draw this diagram. You have to write the characters equation. That equation you have to write. Okay. So load current, armature current, field current. Next equation. Apply a KVL so that you will get E is equal to P plus IRA. Similar way you can find out for shunt generator. Okay. For a shunt generator, you have to make a KVL equation here, right? You have to write a KVL equation here, right? So RMR must start from the armature. That keep in your mind, very, very important. You have to start the armor from here because it is a generator. It generates a supply current power. From that, it is getting divided to the field at the same time the load. So you need to know the IA armature current is equal to, you need to write, is equal to IL plus ISH. Right? Right. So IA is equal to IL plus ISH. Get divide. Now you apply a KVL to the loop, this loop, right? If you apply that, you will get IA into RA, right? V plus the load voltage is V. This voltage is V, right? V plus IA into RA is equal to EG, you will get. Clear? I hope you understand the how to write the equation. Shall I go to question bank? Okay. So this is what mentioned here also, right? So EG minus IARA minus V is equal to 0. EG is equal to V plus IARA. Write a KVL equation in the loop so that you can able to find out induced EMF. Now similar way you can find out for series generator. Series generator have only one loop because it's connected in series. Right? These are all connected in series. So only one loop is available. Load voltage is V. But here two resistance are there. RSC, series field winding resistance, and armature resistance. Two resistance are available. So you need to write VL plus IA into RA plus RSC is equal to EG. You have to write. Right? So that is what written here, right? That's compound long shunt, short shunt. You keep in your mind, long shunt is nothing but series field winding connected in series with armature. It's called long shunt. Series field winding connected in series with armature is called long shunt. Short shunt is series field winding connected in series with the load. It's called short shunt. There's a two types of compound generators. So now it is discussed here. So apply a KVL in this loop. In this loop you apply. So I will get V plus IRA plus IA into RSC is equal to EG. Same as like shunt generator equation you will get. This same loop, sorry, series generator. So V plus IA into RA plus RSC, right? That can be added here. If they have given fresh contact drop, that also kept taken into account while the solving the problem. So while solving the problem, you have to take it into account. As I discussed, short shunt. So here the series field winding, you see, this is series field winding which is connected in series with the load. I see series with the load, it is connected, right? So when you apply a KVL in this loop, right? So you'll have this loop. This loop you have to take, right? You have to take in this loop, right? So V plus IA into RA plus IL into RSC, because series field winding connected in series with the load, not in armature. So IL into RSC you have to take. Clear? Okay, next, going to teach you can you solve this problem? I'll teach you now, right? So 20 kilowatt 200 volt DC generator has an armature and field resistance of 0.05 ohm, 150 ohm respectively. So what it is given, it clearly is given, it's a shunt generator. The 20 kilowatt is indicate that the power, output power, the power value, right? Power value which is given. What is the power value? 20 kilowatt. Input voltage is given 200 volt. Okay. 20 kilowatt power value given, voltage value given, and RA RSC power output is given, voltage is given, RA and RSH value is given. The power developed in armature, EG into IA, they are asking. EG into IA, right? So first you have to draw the shunt generator diagram. The equivalent diagram you have to draw first and indicate the values. Indicate the values. Next, you find out the other value. So how to find out the IA value? How to EG value? EG is equal to, what is the formula here? EG for a shunt generator. Anybody can tell me EG is equal to? When you chat in the chat box, EG is equal to V plus IA into, yes, someone is responded. Yes, very good. Priyadarshi, very good. Thank you. A, right? So to find out this, V value is given. See, V value is given. 200 volt. RA value is given. But how to find out IA value? For a shunt generator, how to find out IA value? See, to find out ISH value for a shunt generator, ISH is equal to, you have studied, V by, someone is chanted. Very good, Priyadarsh, very good, right? V by RSH, right? So that you will get ISH value, shunt field winding current. Because you see, this is your armature, this is your field, both are connected in parallel, right? Right? So in this, right? So here 200 volt, their load, okay, Here load is there. You understand first. This is load, what I am written. So this voltage V is equal to 200. It is given. Load voltage, output voltage is given, right? Okay, va? Next, this current is given, load current is not given, right? But resistance value is given, right? Right. Resistance value is given. Now I wanted to find out this ISH value first. Anything if you want to discuss, please put in the chat box. ISH value, right? So that ISH value can be find out. Next, I can find out IL value because output power is given, output voltage is given. You can find out P is equal to VL, V into IL. From that, you find IL value. Power is given, V is given, find out IL value. So if you know IL value, ISH value, if you add that, you will get IA value. Clear? I hope you all understand that, right? From that, I'll just show you the question bank to you, right? I think someone is asking that, right? I hope you understand this problem. So the second unit, you need to study construction, principal operation, EMF equation, and types of the generator. These questions are very, very important, right? Next, I'll share the question bank. See, important question is here, right? Explain, need sketch, constructional features and principal operation of the DC generator. This is very, very important question. And discover the expression for the EMF of the EMF equation of the generator. That's question. And next question, calculate the flux per pole record on a full load 35 kilowatt 220 volt 4 pole 350 rpm DC shunt generator, conductors 296 conductors arranged in lap connected winding. The armature winding resistance 0.15 ohm, shunt field winding resistance 180 ohm, and there is a brush contact drop 1 volt on each on full load. So flux per pole they are asking. Okay, flux per pole for a generator, right? EMF equation, you know what is EEG is equal to Y Z N by 60, right? So what is EMF equation? Y Z N by 60, right? Just 2 minutes I'll complete, okay? P by A from that, right? So in this, you want the flux phi they are asking in the problem, right? Before that, you need to find out EG. What is formula for EG for a shunt generator? EG is equal to V plus IARA plus contact drop. So that you can find the EG value, substitute EG value, all other data are given. You find out the phi, flux per pole value. Okay. And then different types of excitation is asked in the problem. That's all. These are the problem, the most important problem that will be asked. Okay. Anything else? Can you please put it in the, sir, please teach as fifth unit. Oh, fifth unit. Okay, I'll ask next to tomorrow class, ask some staff to teach the fifth unit. Clear? Already is getting late. Only 1.5 hours time is given. Okay. Please send this question back. Okay. I'll send you through your class teachers. My electrical technology class teacher. Through that, I'll send the question back. Don't worry. Okay. Anything you want to ask, please. Is the only theory is okay for exam? Yes. Shruti, you have to study construction, principal operation, and your EMF equation, and then types of the DC generator. These three questions are very, very important. Okay, so I'm not going to set a question, but you will get one question from this, and all the same time you have to see the problem. So a problem which will be definitely, it will be in the question bank only. Clear? Unit 2 you want to discuss. Okay, it's given, but anyway, already you would have studied this question and all. In the CA exam, you have sent the question, right? The same question only. Faraday's law, elaborate EMF equation of DC generator, define each term. E is equal to 5 is 10 by 16 V by A. Classify the DC generator on their excitation, self separately, self shunt series compound. List of application of the DC generator. List various parts, yoke, pole core, pole shoe, field winding, armature winding, commutator. Describe the role of the commutator. Commutator is going to convert AC into DC. Analyze why DC cylinder is suitable for booster application. This is also asked in the CE exam question. It's a rising characteristics. When the load current increases, voltage boosting, voltage also get increases. So it's a rising characteristic. So it is used for booster application. Classify DC generator is based on the method of excitation. Self-excited, self-separately excited, self-shunt series compound. Analyze the effect of armature reaction. Armature reaction is nothing but, see, when the field and field flux and armature flux both are opposing each other, opposes each other. Field flux, armature flux. So due to that, EMF getting reduced. Field flux reduce, EMF is reduced. This effect is called armature reaction. Okay, please keep in your mind. This is a very important 2-mark question. Armature reaction effect is nothing but effect of armature reaction. EMF will get reduced. Effect of armature. Why it's getting reduced? Armature flux reduces the field flux. So field flux is the main cause for the production of the induced EMF. So EMF will get reduced. This effect is called armature reaction. Explain the method of finding critical resistance speed. This and all would have asked in the CA question itself, right? So you have to find out critical speed. N is equal to the curve you have to draw. From the curve you have to find out DC by AC. Right? I hope this question will be shared to you. Don't worry. Okay? Through your class teachers, it will be shared. Okay, man. Okay. Thank you. Goodbye. Good night. Thank you all. Thank you for joining. Okay. For 10th, 11th question party can we write lamination as answer. 10 and 11. Describe the how to reduce the hysteresis. Hysteresis loss, you have to use silicon steel material. Use of silicon steel material, hysteresis losses reduces. 11th question, laminated construction reduce the eddy current loss. That's all. Okay. So both are different answer. Compare lab and wave winding, that is we discussed. Method of finding critical resistance, that also we discussed. Justify factors which are, what are the factors will affect for build-up in the generator? It should have residual flux and field winding direction. Our residual flux direction should be the same. Critical speed, critical resistance. These are the 4 factors will affect the building of the voltage of the generator. Critical speed, critical resistance, residual flux direction, and field winding flux direction, both should be in same direction. Both the flux directions should be the same. So these are the 4 factors will affect the build up the voltage in a generator. Okay. I think big question, these are the, as I told you, theory question. Problem, you have to see the one problem I teach you now. Right now I have explained you how to solve the problem. Other problem, everything is available in the notes. Please refer the notes. From the notes only the problems are asked. Okay. Okay. Thank you. Anything else? Okay. Thank you. Thank you. Good evening. Good night to all.